In this video we will cover the point-to-point MIMO channel, where we have multiple antennas at both the transmitter and at the receiver. We will first introduce this setup, we will look at some linear algebra results that are useful in order to analyze it, and then we will derive the channel capacity using those results. And we will exemplify some of the properties that the MIMO capacity have. Finally, we will look at transmitter diversity in a slow fading scenario because we can analyze it using the same type of methodology as the point-to-point MIMO channel. So a point-to-point MIMO channel is when we have a transmitter that communicates with the receiver, and the transmitter have multiple antennas and the receiver have multiple antennas. And I will let the number of antennas at the transmitter be k. So 1, 2, down to k. And the number of receive antennas, I would denote them as m. So we have 1, 2, 3, so on down to m. And I will focus on the case when we have constant or deterministic channels, not type of fading channels that I talked about in the previous video. And we can view this as a generalization of the SIMO and MISO channels previously. So in the SIMO case, we have only one antenna transmitter and multiple antennas at the receiver. And in the MISO case, we have multiple antennas at transmitter, but only one at the receiver. So the question is, what is the capacity of this type of channels when we have multiple antennas at both the transmitter and the receiver? And we can expect that the SIMO and MISO capacities that we have derived earlier will be special cases. But we will see that we need a much larger framework to analyze this type of channels. That's why one video is dedicated to this topic. Let's start with some basic notation. We are considering a transmission at time L, and we will later drop this time index. So we have k transmit antennas, and we send one signal at each of them. So at antenna 1, we send the signal x1 at time L, and down at the k transmit antenna, we are sending signal x of k at time L. And the signal that is emitted from a particular antenna is going to reach all of the different receive antennas. And that means that the signal x1L here is going to be multiplied with some different channel responses in order to reach the different receive antennas over there. So this channel from transmit antenna 1 to receive antenna 1 is described by this complex scalar G11. And the channel from transmit antenna 1 to receive antenna capital M is called GM1. So in general, the notation that we have is that when we transmit from antenna K to antenna M, it's GMK, that is the notation for the channel response. And then the signal coming from all of the different transmit antenna is going to be multiplied with different channel responses and added up at the particular receive antenna. So at the first one, we get the summation over several different signals. We add Gaussian thermal noise of the same kind as in all of the examples we have considered earlier, and that gives us the received signal at antenna 1. And we have the same procedure for all of the different receive antennas. We are getting a summation over signals coming from all the transmit antennas, multiplied with different channel responses. We add thermal noise, and that gives us the received signal. So these are the received signal. We have m of them because we have m receive antennas. And we can also write the received signal at antenna M as ym of L at time L. We then get the summation over all of transmit antennas. For the kth transmit antenna, we are sending xk of L. We are multiplying with the channel response gmk. And then we add the noise nm of L. So this is the received signal. And the noise here is assumed to be independent between different antennas and also between different time instances. So what we have here is what we call a memoryless channel, where the transmissions at one time is independent of transmission at another time. So for that reason, we can just treat one arbitrary time and throw away time indices. And then the received signal at the antenna M, ym, is equal to the summation over the transmit antennas, the signals xk transmitted from antenna K. We have the channel response, and we add a noise. And we have equations like this for all of the capital M receive antennas. And to write it in a more convenient form, we will now develop a vector matrix description of this entire MIMO channel. So if we take our M received signal, ym, and we stack them in a vector, y1, y2 down to y capital M, then each of them is this summation over signals transmitted from the different transmit antennas. We are having different channel responses here, and we see that we have 1 down to capital M here. That is where the index of the receive antenna makes difference, while everything else in this expression is the same on every row in this vector here. And then we add a vector with the noise, n1, n2 down to n capital M. And this summation here can also be written as a vector multiplication. So what we have is x1 multiplied with g11, we have x2 multiplied with g12, down to x capital K multiplied with g1k. And we can view this as the first row of a matrix, and then we have a column vector here of length k containing all of the transmitted signals. And we can repeat like this, creating different rows in this so-called channel matrix, and in that way we can represent all of these different summations. And then we have a vector here of length m with the noise at the different receive antennas. So using bold-faced vector and matrix notation, this received signal vector of length m can be written as a bold-faced y. Then we have the so-called channel matrix, capital G, and it's an m by k matrix. So it has m rows and k columns. So the number of rows is representing the number of receive antennas, and the number of columns is representing the number of transmit antennas. And this matrix G is multiplied with a vector x that is containing the transmitted signals. So this is a length k vector. And then we add the noise vector, boldface n, that contains the m receiver noise terms. So instead of writing up all of these different elements here, we can also write this in short form as y is equal to g times x plus n. And this type of description with a channel matrix and different vectors will be very helpful in order to analyze not the received signal at just one of the receiver antennas, but the entire system at the same time. So what is the channel capacity of a system like this? We are considering a case where we're sending a vector x. It goes over a channel matrix G. We add noise, and that gives us the received signal y. And what we would like to figure out is how much information can we send from x to y, given that we have some additive noise here that we can't control. And in general, the channel capacity is defined as the so-called mutual information, which is the information between the transmitted signal x and the received signal y. And we should maximize something like this with respect to the random distribution of the signal x. And we would like to limit the amount of power that we can use when we are transmitting. So we take the squared norm of x, we take the expected value of it because this is a random number, and we want it to be smaller than some maximum energy per symbol q. In general, the mutual information can be divided up into two parts. One is the uncertainty, or so-called differential entropy, of the received signal. And the other part that we subtract is the conditional differential entropy of the received signal when we know the transmitted signal. And we want to maximize this mutual information by selecting x, or rather its distribution, under this power constraint. And what we are disturbed by is the vector n with independent complex Gaussian noise terms having zero mean and n naught as the variance. We could try to compute the capacity by computing this differential entropy terms and figuring out what distribution that maximizes them, but instead of doing that, we will look for a shortcut using some linear algebra and using this matrix vector relationship between the received signal and the transmitted signal. So I will first review some linear algebra results. The first thing that I'm sure you have heard about is eigenvalues and eigenvectors. So consider a square matrix A, which is m by m, and then a non-zero vector u is called an eigenvector of A if you can take u, multiply with A, and what you get is u back, multiply with a scalar value that we call lambda here. And lambda is the so-called eigenvalue corresponding to u. So we are getting a vector pointing in the same direction, but it's scaled. And we can select many different u's. We can take this same vector and multiply it with another non-zero scalar, and we get another u, but we will still keep the same scalar lambda. And based on the eigenvalues and eigenvectors, we can create something called the eigenvalue decomposition. So if the matrix A have m linearly independent eigenvectors, so these are vectors pointing in different directions and they satisfy the requirement of linear independence, then we can take the matrix A and write it in terms of its eigenvectors and eigenvalues. And the way that this is done is that you create the matrix U, which contains the unit norm versions of the eigenvectors. So remember, for each eigenvector there are eigenvectors of different length, but if you take each one of them and you normalize them, so they have length 1, then you put them as columns in this matrix U. And then you take a diagonal matrix D that on each diagonal element contains the corresponding eigenvalues. So the first column is U, is one eigenvector, and the first element in D is then going to be the corresponding eigenvalue. Then it continues like that. And then you take the matrix U with the eigenvectors, and you take the inverse of that one, and you put it on the right hand side, and in this way you can represent this matrix A. And in cases when A is symmetric, so that A is equal to the Hermitian transpose of A, or the conjugate transpose, then it turns out that the inverse of the matrix U is the same thing as the conjugate transpose of U. And this type of matrices that are having unit norm columns and satisfy this requirement is called unitary matrices. So they always have this possibility that if you take U, multiply with U Hermitian, you get an identity matrix. If you take U Hermitian times U, you also get an identity matrix. So these ones are their own inverses as long as you are selecting the conjugate transpose of it. And under that conditions, which happens for symmetric matrices of this kind, then you can replace this inverse of the eigenvector matrix with the conjugate transpose of it. And one can also say that the matrix is diagonalizable because we can take A, we can multiply from the left hand side with U Hermitian, and then we are creating this type of behavior on the left hand side here, and that is bringing only D U Hermitian left. And then from the right hand side you multiply with U to create something like this, and you can then transform the expression like this. So you take a matrix, you multiply from the left and right with different versions of its eigenvector matrix U, and then you create a diagonal matrix D. So this is the eigenvalue decomposition, which you have hopefully heard about before, but can we extend this to non-square matrices? Because we would like to use similar type of results, but for our channel matrix G, which might be non-square because we might have different number of transmit and receive antennas. And yes, there is an extension of this concept called the singular value decomposition, and I will introduce it to you here. So for every complex M times K matrix G, which could be our channel matrix, it can be factorized always like this. G can be written as U times sigma times V Hermitian. U is called the left singular vectors of the matrix. So each column there is called a singular vector. And similar to the eigenvalue decomposition, U is an M by M matrix here. It's unitary. So it satisfies that requirement that U times U Hermitian is an identity matrix. And actually it contains eigenvectors of a matrix. Not G, but G times G Hermitian. So if you create that matrix, you take out the eigenvectors of it, you gather them in U and normalize them, then you get this unitary matrix called the left singular vectors. The matrix V is created in a similar way. This is called the right singular vectors. So each column in V is one singular vector. And this is a K by K matrix, so note that it has a different size than U. It's also a unitary matrix, and it's also constructed based on eigenvectors, but not of G, but of G Hermitian G, which is going to be a K by K matrix. So from this matrix, you take the eigenvectors, you put them in the matrix V in each of the columns, and make sure that they are normalized so you get a unitary matrix, and then we have created U and V Hermitian. And what remains to describe is this matrix sigma. And this one contains the so-called singular values, which is something similar to the eigenvalues. So sigma is an M times K matrix, just as G, and it's so-called diagonal matrix or rectangular diagonal matrix. So it means that everything that is on the main diagonal is non-zero and everything else is zero. So if this is a non-square matrix, we fill in with zeros. The singular values on the diagonal are always positive, and we will assume that they are ordered in a decreasing order because that will be helpful for us later on. So S1 is the largest one, it's on the first element on the diagonal. Then we have S2, which is smaller, S3 and so on, and the smallest value is S with a subscript minimum of M and K, because that is how large the square block of this matrix is going to be. And then we fill in with zeros in that dimension where we have more antennas. And also this element is going to be greater or equal to 0. So there are no negative singular values, but some of them can actually be 0. And the singular values also are connected to eigenvalues of G, or not actually G, but G Hermitian or G Hermitian G. Both of those ones are going to have eigenvalues, which are equal to the squares of these singular values. And then the one of these two that is larger than the other one, because we have more antennas in one of the dimensions, is also going to have some zero-valued eigenvalues. We can use the singular value decomposition to diagonalize the MIMO channel and turn it into multiple parallel channels that are not interfering with each other. And that is the purpose of this slide. So remember that U and V are so-called unitary matrices. If we multiply with them, we can multiply again with the Hermitian transpose of it, and then we will get the same result back again. So therefore, we can do some so-called non-destructive processing by using U and V, knowing that if we do that, it's not going to ruin the optimality of how we design our system, because we can always undo these processes again. So what I will do first is that I will select a pre-processing where the transmitter signal X is created by taking the right singular vectors in the matrix V and multiply them with X tilde. So X tilde is the vector with data, but what we actually transmit X is a product between V and X tilde. Then at the receiver, when we are getting the received signal Y, we multiply it with U Hermitian in order to form a new received signal Y tilde. And we can write it like this, that the signal X that we're transmitting is formed at the transmitter by taking X tilde and multiply with V. Then X is multiplied with the channel matrix G. We add a noise N to get Y. And at the receiver, we do this receiver processing. We take Y and multiply it with U Hermitian to create Y tilde. And why do we create it like this? Well, Y tilde is going to be U Hermitian times Y, and Y is this received signal, G times X plus N. And let's now expand this expression. X is equal to V times X tilde. G can be expanded using its singular value decomposition like this. So we have G Hermitian, we have G written as its singular value decomposition here, and then X is V times X tilde. That was something that we assumed. And then if we take U Hermitian times N, this is our new noise vector. Let's call it N tilde. And one can also show that if N contains IID complex Gaussian elements with zero mean and N not that is variance, then N tilde will contain the same type of distribution. Finally, since U is a unitary matrix, U Hermitian U is a identity matrix. So this part goes away. And V is also a unitary matrix, so V Hermitian V is also turning into an identity matrix. So this part is also going away. So here it says just sigma times x tilde plus a noise vector n tilde. So that is what we have now. Y tilde equal to sigma times x tilde plus n tilde. We let capital S denote the number of non-zero singular values. So these are along the diagonal on sigma. And the first S element will be non-zero and the remaining ones will be zero. And capital S is, by the way, the rank of the matrix G. We can now take this vector matrix representation and divide it up again into different equations. So we have m received signals, so y tilde is going to be m-dimensional. And the first one will contain one singular value, S1, multiplied with x tilde 1, which is the first transmitted signal in the x tilde vector, plus one realization of the noise. And then we get the same type of expression like this for all of the capital S non-zero singular values. So these are the first S rows in y tilde. If we have additional rows in y tilde after that, so for S plus 1 to capital M, then we only gonna have noise there, because then the singular values will either be zero or non-existing if we have a matrix sigma here that have more rows than columns. What is interesting here is that we have S received signals that are containing one transmitted signal multiplied with one singular value, added one noise. And these are our useful subchannels, and we have capital S of them, and they only contain one transmitted signal each. So there's no interference between different elements in the x tilde vector. Then we have some additional received signals that only contains noise, so there is no information in those ones. They are useless subchannels. So let's throw away this second category and keep the first category. And one way of representing this is as capital S parallel channels. So we can write like this. The first one, x1, is multiplied with s1. We add a noise n1 tilde to get y1 tilde. And we continue like this down to the capital S subchannel, where we have x tilde s multiplied with s capital S, which is a singular value. And then we add noise to get the received signal. And you might recognize that something like this is just like a MISO channel, where we send one scalar, we multiply with a channel response, we add a scalar noise to get the scalar received signal. So suppose that we are assigning a particular amount of power to each one of these subchannels. We have the power Q to divide between them, and for the moment, let's assume that Qk is the amount of power that we assign to subchannel K. Then that subchannel is just a MISO channel, and we know how to compute the capacity of something like this. We call it Rk here. It's log 2 of 1 plus a SNR, signal to noise ratio, containing Qk, which is the energy per symbol that we're transmitting with. We have the channel response, which we square, so we Sk square, and we divide by the noise variance N0. We can do this for each of our parallel subchannels. The channel capacity C can now be written as a summation over our S subchannels, where we take the achievable rate on each of them for a given Qk, and then we would like to maximize this expression with respect to Q1 to Qs, the power that we assign to each of the different subchannels. And we do it such that the sum of the elements are going to be equal to Q, the total amount of power that we have available. And this is a so-called optimization problem, and I will not in this video go into details on how we are computing the optimal policy of how to allocate the power between the subchannels, but instead I will present the result. The optimal power allocation is like this. So after solving this optimization problem, Qk, which is the power that we assign to subchannel K, is going to be the maximum of two numbers. Either 0, because we can never transmit with less energy than 0, or it's this number here, which contains mu, which is a parameter that we need to select, and then we have N0 divided by Sk square, which is something that we're subtracting. And notice that this is something that is appearing in our sign to noise ratio, but in the other direction. So sk squared divided by n naught, upside down. And mu is a parameter that we are increasing such that we are eventually getting the summation of all the q, q1 to qs, to be equal to the total power q that we would like to assign. So what does this mean? Some of the properties that we can see here is that the larger the singular value sk is, the smaller this term that we're subtracting is going to be, because then we are dividing with a larger number. So if everyone gets the power mu minus a number here, then if that number is smaller, we assign more power. So that means that the strongest subchannel with the largest sk will get the most power, and then the power will be smaller and smaller the lower the singular value is. And some subchannels might even get 0 power because of this term that we subtract being larger than the value of mu that gives us equality in this term. So this is called water filling power allocation because this process can be viewed as taking water and fill a tank with that water. So here's the description of that. Mu is called the water level, and each subchannel, 1, 2, 3, 4, have a height here on the bottom that is this n naught divided by sk squared. So the strongest one, S1, have the smallest height, then we have larger one, and the larger one. And the power allocation is then that we start pouring water into this tank, and first the water is going to be appearing in the strongest subchannel. Then after a while it spills over so it reaches both the strongest and the second strongest. Then we increase the water even more until it reaches the third one, and potentially in this case it also will reach the fourth one eventually. But when the water level mu is such that the blue area here is representing all the power we have available, well, then in this case subchannel 4 didn't get any power at all. So we can see the strongest one gets the most power because that is the amount of water above it. Then the second strongest channel gets the second largest amount of power, and then it continues like that. With this water filling analogy, we can understand what happens when we have low SNR and high SNR. We can also be viewed as having little power or a lot of power. If we have little power or low SNR, we are starting to fill up with power here, but we only put power on the strongest subchannel because we never reach over this limit when we start to use the second one. At high SNR, however, we have a large amount of power. So we start to fill up the first one, the second one, the third one, the fourth one, and then we continue filling up. And as the water level is continuing increasing here, we will approximately have the same power in all of them. It will always be that the strongest subchannel get a little bit more, but the height differences at the bottom of this pool will eventually play very little role when the amount of power is large, so that we are filling up with a lot of water and reach far up here. We can also analyze these behaviors mathematically. So at high signal to noise ratio, we concluded that it should approximately be optimal to take our power and divide it equally between the different subchannels. So say that we have capital S subchannels with non-zero singular values. Then we take Q1 equal to Q2 equal to Qs, and we take the total power Q and we divide it with the number of them, capital S. In this case, our capacity expression can be approximated such that we have a summation over all the subchannels. We have log 2 or 1 plus a SNR. I'm using now this form Q divided by N naught. I will call it SNR. And then we had SK square, and we will get an S here. So this Q divided by S as the power allocation, that is this Q, and we have this S here. So the approximation here is only that I'm claiming that this equal power allocation is the optimal thing. Then I will do a second approximation here, which is removing this 1 here, because the SNR is very large. This is a dominating term inside the logarithm. In that case, we can take this summation over log 2 of SNRs and write it like this. We have S terms that all of them are log 2 of SNR. Then what remains is a summation from 1 to S of the logarithm of sk squared divided by s. So this is what we are writing as the second term here. And what I am interested in is this first term here. The capacity is growing as log 2 of SNR. That's something we have been seeing before. That happens for a SISO channel. But in that case, there is no factor in front of the logarithm. And that is what we are getting here. This is the so-called multiplexing gain. At high SNR, the capacity is growing as log 2 of SNR multiplied with the number of subchannels that we're having. So the first term is proportional to S, which is the rank of the matrix. And it's smaller or equal to the minimum of the number of transmit and receive antennas. So the minimum of that is putting a limit on how many subchannels we can have in a system like this. And if G is a good matrix in the sense that it has full rank, then we are getting a multiplexing gain that equals the minimum of the number of transmit and receive antennas. And in some cases G might be rank deficient, then we are losing some of the multiplexing gain. At low SNR, let's now assume that the singular values are all different. So S1 is strictly greater than S2, which is strictly greater than S. In that case, we will have different levels of the bottoms of this tank, and that means that we will assign at low SNR all the power to the first subchannel and nothing to the remaining ones. Our capacity approximation now is that if we assign this approximately optimal power allocation, then when we have a summation over all different subchannels, we only keep the strongest subchannel because that's the only one getting power. Then we get log 2 of 1 plus SNR S1 square. So this is the squared singular values of the strongest subchannel. And at low SNR, we can say that the log is approximately linear. So we get log 2 of E times this SNR times S1 square. So here we see that there is no multiplexing gain. Even if we have a high rank of the channel, we don't have enough power to utilize all the subchannels. So we focus our attention on the strongest subchannel. We still can say that we have a beamforming gain because log 2 of E times SNR, that is what we would get in a SISO channel. And now we multiply it with S1 square, which is the largest among all the singular values. So we get the benefit from being able to select one particular directions that we are beamforming in and using the largest of the singular values. Let's now compare the SISO channel capacity, the Simon MISO case that were providing the same capacity, and this MIMO capacity that we have just derived. And to make it simple, we assume that whatever channel response we are dealing with, its absolute value is always going to be equal to 1. Then the SISO channel capacity, C, is log 2 of 1 plus the SNR. And then we multiply with a 1 here, which is going to be the square of the absolute value of G. In the SIMO and MISO case with M antennas, either at the receiver or the transmitter, the capacity is the same, log 2 of 1 plus M, which is number of antennas, because if we take all of those channel coefficients, we take the squared norm of the channel vector, we have each of the channel component are giving us a 1, then we get M, and that is the beamforming gain. Then we multiply that with SNR and we have our capacity. In the MIMO case, we assume that we have the same number of receive and transmit antennas. And it's actually not enough to assume that all the elements in the channel matrix have an absolute value that's equal to 1. We also need to consider what are the phases, because that is what is determining what the singular values are going to be. In the ideal case, all the subchannels are equally strong, and therefore all the singular values are equal to square root of M. So let's look at that ideal case now, and then we will look at a different case later. In that case, the capacity will be equal to M, which is the multiplexing gain. It's the minimum of M and K, and they are the same. So let's just write M here to be consistent. And then we have log 2 of 1 plus the SNR. Why don't we get an M inside here? Well, we actually have a square root of M that is squared, so we get the squared singular value, but then we are taking our power and we divide it over our M different subchannels. That is cancelling out that term again. So therefore we see that we get log 1 plus the SNR, the same expression as in the SISO case. But we have the multiplexing gain in front here. And this is also known as the pre-log factor because it's something that is appearing in front of the log. Here is now a simulation of this. We have the capacity here in bit per symbol. We are varying the SNR. The lowest curve is the blue curve here, which is the SISO case. Then if we are introducing a SIMO or MISO case with 4 antennas, so m is equal to 4, we get the red curve, and this curve have the same shape as the SISO curve, but it's moved towards the left. How much? Well, we have 4 antennas that represents a 6 dB gain here, so we have actually shifted the curve 6 decibels to the left. And that is what we are getting from a beamforming gain. In the case of a MIMO channel, we are not getting that type of beamforming gain here, but we are getting a much better slope. So at low SNR, when we're only using 1 of our subchannels, then the red and the black curve here, where the black curve is represented in the MIMO case, they are going to be overlapping. But as we are increasing the SNR, we eventually see this high SNR behavior, where we have a scaling with SNR that is much faster than in the SISO case. So when we have 4 antennas, we get 4 times log 2 of 1 plus SNR. So if we have a blue curve with this slope, then the black curve have a 4 times steeper slope. And the higher SNR is, the larger the gap is. And this is really the main selling point of point-to-point MIMO channels, that we get this much steeper slope, and therefore at high SNR we can get a much, much higher capacity. Let's now consider another example, namely a line-of-sight channel, because those channels are known to have high SNRs. Because when you don't have any scattering and anything like that, the signal is going to be reaching you with a much larger amount of power. There's no power that's disappearing along the way. And let's assume that we have a transmitter with K antennas in a uniform linear array, and we have a receiver with M antennas also in a uniform linear array. And the transmitter and receiver are far away from each other. That means that the angle of departure for every antenna at the transmitter towards the receiver is going to be this angle here. It's the same one for all of them. That happened approximately when the transmitter is far away. And at the receiver we have a common angle that is describing the angle of arrival from the transmitter to all the receive antennas here. And we can then compute every element in the channel matrix using the same type of tools as we had in the previous video. I'm not going to cover all of the exact details in the derivation, but assume that we have a reference antenna, 1 at transmitter and 1 at the receiver, and then we get a 1 as a channel multiplied with square root of beta, and this is a common channel gain between each transmit antenna and each receive antenna. It's approximately the same because the distances are approximately the same. But then we can compute different phase shift for different antennas based on the length of these parts here in the triangles, and we get this matrix over here. And interestingly, this can be written as an outer product of 2 vectors. The first vector here is the channel vector that we will have from the reference antenna at transmitter to all the receive antennas. And the second part here is the channel from all our transmit antennas to the first receive antenna. And then we also, of course, need to involve the channel gain to say that. But the important thing is that we have an outer product of 2 vectors, which means that G can be viewed as having singular value decomposition with only 1 non-zero singular value. And the corresponding singular vectors are these 2 vectors. And the rank is then equal to 1, and the strongest singular value S1 is going to be square root of beta, and then if you normalize these 2 vectors to have length 1, we also get a square root of m from this part and square root of k from this part. So the largest singular value is square root of beta times m times k. And what this means is that we have a rank 1 channel, so the multiplexing gain is going to be 1. And the optimal thing is to assign all the power to that subchannel. So that means that the capacity is log 2 or 1 plus the singular value squared times SNR. So here we have beta times m times k. We can compare this with the SIMO and MISO cases that we have been considering before. Then we get beta times m, and we can ignore the beta if we like to. The important thing is that this m times k is the beamforming gain in the MIMO case, and m is the beamforming gain in the Simon MISO cases. So we get the product of the number of transmit and receive antennas here, and here we only get one of them because we only have multiple antennas at either transmitter or the receiver. And of course, this is special cases of the MIMO case. But we have a larger beamforming gain when we have multiple antennas at both the transmitter and the receiver. So even if we have a line of sight channel with rank 1, we still benefit from having multiple antennas. That's the end of the point-to-point MIMO part of this lecture, but I will wrap up by considering the slow fading case again, now with multiple antennas at the transmitter side, because we can analyze this with the same type of tools. So in this case, we have a received signal, Y of L, at the single antenna receiver, and we have two transmit antennas to keep it simple. And we have G1 and G2 being the channel from the two transmit antennas to the receive antenna. We are sending signal X1 of L and X2 of L at time L. So these are signals from antenna 1 and antenna 2. And then we add noise. And this is slow fading channel, which means that the realization of G1 and G2 are random. The receiver knows them, but the transmitter doesn't. It's the same realization throughout the communication. And normally we would let the transmitter select the vector here with the X values to be based on the channel, but we can't do that here. So what else can we do? Well, what we will consider is transmission over two time instances, Y1 and Y2 at time 1 and 2. And the channels are the same in both cases. Here is the vector that we're transmitting at time instance 1, and at time instance 2 we have this vector. And we put all these things in a matrix that we call capital X. And here is the noise at time 1 and time 2. And what we will consider now is called space-time coding, because we are both using space in terms of multiple transmit antennas and time because we have two time instances. So the idea is that we should select X in a particular clever way, not based on the channel, but still so that we can achieve some gains of having multiple transmit antennas. And in space-time block coding, there are many different ways of selecting X. Here is one particular example called the Allocation code, where X is selected, so it contains two pieces of information, X tilde 1 and X tilde 2. And they are put into X here in a particular way. So transmit antenna 1 is first going to send the first message and then the second message. While antenna 2 is first going to send the second message with a minus sign and a complex conjugate, and then the first signal with the conjugate. And then this 1 divided by square root of 2 is making sure that we are keeping the same power every time we transmit. If you write the received signal at time 1 and the conjugate of the received signal at time 2, then using this X we can write the received signal this way, and then we can simplify the expression so that we are getting a vector with the transmitter signal 1 and 2 with the conjugate. Here we have a matrix containing the different channel coefficients, and then here we have a noise vector. And the reason that I rewrite it like this is that now it looks very much like a 2x2 MIMO channel. Two received signals, two transmitted signals, a channel matrix, and a noise vector. And moreover, this channel matrix that I will now call G tilde, it has an interesting structure because these two columns are linearly independent. So if we just normalize it by dividing with the norm of G, then this matrix here can be viewed as a unitary matrix. And then what remains is this 1 divided by square root of 2, and then we were dividing with the norm of G, which is the channel vector, so we can write a diagonal matrix here that is taking care of that scalings. So then this whole thing is just going to be G tilde. And then if we want this to look like a single value decomposition, then we have a unitary matrix U, we have a diagonal matrix with singular values, and then we just add an identity matrix on the right hand side, which will then represent V tilde. And if we would like to communicate over a 2x2 MIMO channel of this kind, then the transmitter needs to know V tilde, because it's going to take its signal vector that it would like to communicate and it will multiply with V. And V tilde here is just an identity matrix, so the transmitter would know that one without having to actually know the channel. So it knows how to transmit in order to achieve this kind of capacity. The only problem is it doesn't know what the capacity value is going to be, because that will depend on what the realization of G is. For that reason, the ideal capacity in the MISO case, if we know the channel, is going to be log 2 or 1 plus Q divided by a naught, that's the SNR, and then the singular value squared is a squared normal channel vector divided by 2. If we compare that with the ideal capacity in the SIMO case that we considered earlier, we were getting similar expression, but there is no division by 2 here. And the reason that we have this division by 2 here is that we are not getting a beamforming gain because we don't know the channels. We can't align our transmission with that one. So we are losing the beamforming gain. But apart from that, the capacity expression looks the same, so we're just having this loss in the signal to noise ratio. And we can characterize the outage probability in the same type of way. Same behavior as before, it's just that we will have only half of the SNR. So we can expect to get a diversity gain, but no beamforming gain. And that is shown in this graph here, where we show the outage probability on the vertical axis versus the SNR and dB scale. We have the black curve, which is the SISO case. Then we have the blue curve that we have analyzed earlier. This is the SIMO case with 2 antennas. And we see that we have a better slope. That is because of the diversity gain. And then we have the red curve, which is for the MISO case. It has the same slope as the SIMO case, which is showing that we are getting the same diversity gain. But it is moved towards the right, and it's moved by 3 dB, because that is the equivalent of having only half of the SNR. But we can still, with multiple transmit antennas, achieve diversity even if we don't know the channel. And we can extend these examples to having more than 2 transmit antennas. There is a big area of space-time coding, but we will stop here and just show that we can achieve a diversity gain even if we don't know the channel at the transmitter side. In this video, we considered a point-to-point MIMO channel, and we saw that if we have k transmit antennas, then we should use the k eigenvectors of G Hermitian G as our beamforming vectors. That creates k parallel channels. Without any interference between them, we allocate our total transmit power between them using water filling. At high SNR, we use all of these parallel channels, and we achieve a multiplexing gain. So we increase the capacity proportionally to the minimum of the number of transmit and receive antennas, or at least up to that. At low SNR, we only use the best of the channels, and that gives a beamforming gain. We also considered the slow fading scenario, where we have multiple antennas at only the transmitter, and we saw that we cannot get a beamforming gain if we don't know the channel, but we can still get a spatial diversity gain by using space-time block codes, in particular the Alamuti code, and we can analyze that using the same methods as for the MIMO capacity.